Hello everyone. Unfortunately, 3 days ago, a deadly tornado struck the suburbs southwest of Union City, Michigan. And this tornado was quite a shock. Well, why? First of all, Michigan hadn't seen a tornado this strong in quite a while. The last legitimate, in my opinion, near F4 tornado candidate in Michigan happened on March 20th of 1976 in the suburbs of Detroit. That is nearly 50 years ago. And not only that, but this tornado happened in early March, which is an extreme climatological anomaly. Just how extreme of an anomaly is this? Well, this map shows all tornadoes in Michigan that we know of from March 1st to March 15th, in the first half of March. You can see that there's not many, although the EF3 tornado near Dexter from March 2012 sticks out here like a sore thumb. But then, let's see how many of these tornadoes caused fatalities. None of them have. We have data going back to the 1880s on this stuff. And the Union City tornado 3 days ago was the first tornado in Michigan history, early in the first half of March or earlier, to cause fatalities. And not only did it kill someone, it killed 3 people. This is a huge climatological anomaly. So, how does a Michigan tornado in early March, 1, get that strong, become the state's first F4 contender in 50 years, and 2nd, become the first tornado in the state's history to cause fatalities before March 15th? Let's find out. We always start with the big picture. And on March 6th, there was quite a severe weather setup. You had a typical Colorado low here that came off the Rockies, which was setting up a big normal dryline threat in Kansas and Oklahoma. However, one thing that really stands out is how big this warm sector is, especially for early March. First of all, for early March, the Gulf is very moist. There's 70 dew points all over the Gulf. And there's 60 dew points getting as far north as Michigan, Iowa, and northern Illinois. For early March, that is quite anomalous. Let's look at the 500 millibar flow to see where the warm sector and usable flow for severe weather initiation are co-located. Well, first, you'll see that the obvious area is the Kansas and Oklahoma dryline threat. They're pretty co-located, and you can see quite good flow here and here. So that's a severe weather threat. And let's look at the 850 millibar map to back that up. You can see a strong 850 millibar wind here, and you can see that difference. That lower level jet will make this area a tornado threat. So threat number 1. Now you can see just how far inland the moisture got. Let's look at central Illinois, northern Iowa. And you can see that too is co-located with favorable 500 millibar flow. But let's look at the 850 flow. See how, especially in northern Illinois and Iowa, the wind barbs don't really change direction. They remain pretty similar to the southeast. That precluded the severe weather threat in that area from becoming tornadic. However, there was one more area. You can see even up here, the moisture got as far north as southern Michigan. 60-degree dew points in southern Michigan in March is quite an anomaly. And look, it was co-located with some 500 millibar flow. And as you can see with that warm fronts are always key areas for severe weather development. Why? We will go into that later, as the warm front plays a key part in this tornado's formation. And you can see that was co-located with 500 millibar flow. But if you look at the 850, you can see that the wind barbs here are completely different. Here, they're more west-southwest, but here, they're clearly southwest. The change here is much bigger than it is in central Illinois, which makes this warm front threat an area to watch. Let's look at some soundings from the severe threats. This is a sounding from central Oklahoma in association with the dryline threat. I mean, this is pretty classic for March. You have the inverted V profile, which isn't surprising because most of the air being advected into the dryline was coming from western Texas, which is bone dry. So that's not surprising. And you can see here, although there wasn't much lower level shear, there was a lot of CAPE, 4,659 joules of MLK. And explosive supercells did come off of the dryline, which was the primary initiating mechanism, and one of them produced an EF3 near the towns of Beggs, Oklahoma. Let's look at the Illinois severe threat, and this is surprisingly kind of falling flat. there's a few things that jump out here as negatives for tornadoes. First, well, the winds, there's not much lower level directional wind shear change, and you can see the photograph is quite straight. It's not impressive. And also, that area is just like so dry because Illinois was more directly in the flow. If you trace the wind barbs back, you can trace it back to this area, to the dry Oklahoma and Texas panhandle. The air being convected there was pretty dry. The air being convected in Michigan, though, if you follow the wind barbs, it kind of falls out around this area. So the air that's being taken from here doesn't really make it across. So there's much less dry air in the Michigan part of the warm sector than there was in the Illinois and Iowa part. That's another plus for Michigan. And let's look at the 500 millibar flow. Let's go back to 18Z and look at the warm front threat in more detail. Because the dryland threat's already obvious, the Illinois threat isn't there, but something sneaky could happen around the warm front, right? Let's look. There's good 500 millibar flow over northern Indiana and southern Michigan and most of Illinois, which is a good plus for, convective initiation. Let's look at the 850 millibar flow. As we said here, the wind barbs barely change, but over here in Michigan and northern Indiana, they change a lot more. There's a lot more change here between 850 and 500 than there is here. So there's more low-level shear here. And let's look at it with the warm sector. There are 60s dew points in that area. So because there's a larger wind shear over here, and we have a usable warm sector over here as well, this small sliver of northern Indiana becomes an interest point for convective initiation. And, well, did that happen? Yes, it did. You can see here, based off the previous three maps, that convection did indeed initiate in the warm sector along that warm front. And as it moved to the north, how would we expect this convection to evolve? Well, let's look at what the models have. Let's look at what happened using the RAP. You can see the 500 millibar flow moved into Michigan and became more plentiful over the area. That's favorable for sustaining that convection, and if a storm does go up, that 500 millibar flow is going to help sustain it. Let's look at the dew points. As the day went on, the warm front lifted north into Michigan, and if a storm were to initiate here earlier in the day and move northeast, it would still stay within the warm sector around that warm front and stay near that warm front sphere of influence. And let's look. The storms did just that. The warm front lifts to the north throughout the day, to the northeast, and the convection stays in that warm sector and stays completely isolated. And eventually, as it moved into Michigan, it moved closer and closer to where that warm front was set up, and it began to show tornadic tendencies. Now, there's something striking about this image. The storm is completely isolated. If there's 60s dew points at 500 millibar favorable flow, there should be more storms, right? Why aren't there more storms here? Why isn't there something ahead of this supercell? Why is it just this storm? Let's answer that question now. We've established that 500 millibar flow is good over the whole area, which makes it kind of perplexing. But a key figure in this part, at least for Michigan, why there aren't storms ahead, is the warm front. The warm front was only draped over the southwestern corner of the state, not over here. So that's why no storms were going up in this area. We're going to prove that with a sounding in a second. Also, let's prove that now. You can see a reading, which is based off of this, beyond the warm front. The photograph is good. Very good for tornadoes, a lot of lower level streamwise vorticity, but if you look at the profile, it's completely stable. It's out of the warm front, nothing is initiating there is no instability. Let's look further south. Why are these showers staying as showers and not blowing up into supercells as well? Well, let's look. This is where the warm front becomes so exponentially important. One, notice how there's less low-level shear here, south of the warm front. Basically, at the immediate vicinity of a warm front, you can see how the wind shifts from slightly to the west to more to the east. One, around warm fronts, winds change directionally, and they usually change in a way that causes more streamwise vorticity and a more lower level wind shear in the immediate vicinity of a warm front. Also, you can see the photograph here is pretty straight. There's not much change, so for tornadoes, that's a minus. And also, it's quite dry here. There's a lot of dry air down here, and especially down here, there's an inverted BV profile. So your storms here are working against a lot of dry air and an unfavorable hodograph for tornado development. Nothing tornadic is going to come from here, and that dry air was successful in keeping these storms from doing anything. But what about Centreville? Let's look along the warm front. If the dry air here was keeping these storms from becoming severe, why didn't it work for here? This is why, again, the warm front is so important and favorable for tornado genesis. And the reason behind this lies in physics. First of all, there's less instability here, but around a warm front, three major things happen. One is the wind shift we talked about earlier. There's more wind shear in the immediate vicinity of a warm front. Two has to do with physics. At a warm front, there's cold air to the north and warm air to the south. The warm air to the south is rushing to the north, and it's hitting that cold air at the warm front. Well, let's go back to physics. Warmer air, as you know from physics, is less dense than cold air. So when it goes north and then runs into this massive cold air sitting here, it gets forced up. That causes enhanced lift in the immediate vicinity of a warm front and not much else. This enhanced lift was a key reason why this supercell was able to survive as long as it stayed near the warm front. And finally, the third thing, around the warm front, temperatures decrease as near a warm front. And, well, it's called a warm front for the reason. The air to the south, or within the warm front, is warm, and the air to the north of it is cold. And as you approach the warm front, the air temperature decreases. Because the temperature decreases, because it was colder near the warm front than it was further south, the air aloft, right near the warm front, is more saturated. There's less dry air, and especially at the surface, there's no inverted V profile there. Because it's more saturated, it is far easier to sustain supercells and to get supercellular development in a saturated warm front environment than something dry further south. So those are the three main reasons why a warm front is so important and favorable for tornado genesis. And also, let's look at the climatology. It's March 6th and instability is still quite lackluster. Even around the warm front, instability is quite lackluster. So that's why, once that there was enough instability to sustain a supercell, not really to develop anything else, because the storms here were getting shunted by dry air, and there wasn't much else going on north because there wasn't enough instability to sustain multiple storms. Only one storm that was able to go up earlier in that favorable spot was able to stay active in the warm sector at the time. So you had a lot of favorable things working for it. However, there were some unfavorable things as well. You'll notice that if we go all the way back, this flow is not that strong. It's usually not 80 knots, which is typically what you would want for long-track tornadoes. Well, 60 knots is, one, enough to get supercellular development, and because of the climatology preventing any other storms from going near it, it had no competition. Also, lift wasn't really a problem, and being efficient enough to produce tornadoes wasn't an issue when you have physics working at your advantage, with the dense air pushing the less dense air that's running into it up, creating localized lift. So let's weigh it. So first you have localized lift from the warm front because of physics. That wind shift at the warm front causes more lower level directional shear. There's less dry air in the environment at around a warm front is more saturated because temperatures decrease as you get closer to that cold warm boundary. And because there just wasn't much instability, and because of the time of year you really don't see that much instability, there was no garbage convection. Also, the warm front's area of influence is really, really small. So the area favorable for tornadic activity and supercells was tied to that warm front. Well, what was working against it? Well, the 500 millibar flow wasn't particularly strong, but that was overcome by the localized lift from the warm front anyway, and the instability was a bit shallow, especially the lower levels, so usually that wouldn't be good for tornadoes, right? Well, there was enough instability to allow the supercell to thrive while preventing anything else from going up, so that ended up being a huge plus. So who wins out? Well, let's let the atmosphere tell us the answer. Well, that supercell produced a tornado pretty quickly near Edwardsburg, Michigan. This was an EF1. And then, as it went further, it produced another tornado, this time an EF2 near the town of Three Rivers. So clearly, the warm front is winning out. This supercell is producing tornadoes, even significant tornadoes. The warm front is clearly winning. And then eventually, after the Three Rivers tornado dissipated, which was an EF2 that hit the town, the supercell began to cycle again as it approached Union City. One thing that was notable about the Union City tornado was how quickly it formed. And because we've already established that this is a low cape high shear environment, or high shear low cape HSLC environment, let's look at something geographically that I noticed about these tornadoes and how they form. Let's look at the infamous Cookeville tornado. The supercell, prior to producing the tornado, had developed a strong mesocyclone on radar, but that mesocyclone 1 remained similar in intensity, and 2 didn't really do much until it suddenly dropped the tornado right as it approached Cookeville. Or was it so sudden? Let's look at this annotation. Here, the terrain is noticeably rougher and more hilly, but as soon as the mesocyclone left that area and went into flatter terrain, the tornado quickly dropped. You can see right here was the first tornado damage. As soon as the mesocyclone got into a flatter terrain, the tornado dropped and quickly became violent. Why? Let's look at another case of this. The infamous Valonia, Arkansas EF4, which I personally think was an EF5, but that's another story. You can see here that the damage path remains quite disorganized, and it's not really efficient, but as soon as it exits the hilly area, the damage suddenly becomes confined, it suddenly becomes very well defined, consistent, and extremely violent. So, what happened? Well, one of the most important things in tornado dynamics is the RFD. When you have rough terrain in the way of the RFD, as you did here, it will struggle to wrap up. It is far easier for that RFD to get to the developing tornado and complete tornadogenesis in a flat and smoother area than in a rough area. So, I think that the mesocyclone not waiting until it entered a flat area to suddenly produce a tornado was no accident. As soon as the mesocyclone entered a flatter area, the RFD was finally able to get and wrap around that mesocyclone and produce that tornado, just because in flatter and smoother terrain, there is less in the RFD's way. The tornado here had already formed, but it remained inconsistent until the tornado entered a flatter area. As soon as it entered that flat area, that RFD was able to rotate around the tornado more tightly, make it far more consistent, and allow it to intensify heavily. With this notion in mind, let's keep going forward. You will notice that, similar to the Cookeville tornado, the Union City tornado's mesocyclone remained pretty similar in intensity. Like you see, it's pretty strong, but no tornadoes forming. And then finally, as it approaches Union City, the mesocyclone suddenly tightens up, and the tornado forms quite quickly. Why did the tornado suddenly drop right as it approached Union City, even though the mesocyclone was pretty consistent in the frames before that? Let's look at the geography. Here's another photo showing the rapid intensification. Why did this tornado become so strong so quickly, even though the mesocyclone had been consistently strong in the 20 minutes leading up to this tornado forming? Look at this. This image was taken when the tornado was kind of early in its life. When it had just begun to form, let's fast forward 1 minute and 14 seconds. Look at that. In 1 minute and 14 seconds, this tornado went from this weak funnel to a high-end EF3 that was doing damage in slabbing neighborhoods. How does this happen? With the notion of rough and smooth terrain and how it relates to the RFE from earlier, let's look at the map. And more specifically, first, you will notice that there is a huge lake southwest of Union City. Let's annotate the tornado track on top of it. This was approximately the tornado's track. The official survey revealed that it actually started over here, but it didn't become noticeably strong until it reached this area. Once the tornado came here, it became quite strong, and this is where the worst damage was done, in that area specifically. So, why did it become strong all of a sudden? Remember the idea of friction and the RFD. In rough terrain and in forested terrain, there's way more in the way of the RFD. And that friction prevents the RFD from wrapping around the tornado and helping it intensify and become well defined. Well, I'll tell you that there is no less frictional surface than water. Water is perfect for an RFD. There's nothing in its way. There's nothing preventing it from wrapping around that tornado and making it significantly strong. As soon as that tornado neared water, that RFD was finally able to get uninterrupted, no friction access to that developing tornado. And it was able to wrap around it super, super quickly and strengthen that tornado at an extremely rapid pace that was far greater than what the storm's dynamics would have been able to do on their own, simply because water has no friction and the RFD was able to exploit that. Let's look at the damage. The tornado first became strong as it, first approached the lake. This home right here was among the first homes to be hit hard by that tornado. And you can see the significant damage continues here. That home was destroyed because the tornado was moving this way. And to the south of that tornado is a lake. And again, water, which is no friction, which offered no friction or resistance to that RFD. Also, the lake at the day of the tornado was frozen. And a frozen lake offers even less friction than one that's melted, as waves offer a tiny bit of resistance. Anyway, as that tornado continued to the north, it became quite strong. It weakened a little bit, but then as it hit this subdivision, it became unbelievably strong. Let's zoom in and analyze this damage more. Here, the damage becomes a little bit less intense, and then you can see here that this grove of trees was still intact, and this home was slightly still intact. But then, as soon as it crossed into this area and entered that subdivision, again, all the obstructions to the south abated. And again, the only thing when the tornado reached this subdivision to the south of the tornado was water, which offered no resistance. That allowed that RFD to really quickly strengthen. If you look at videos of this tornado, you can see waves and stuff coming into the tornado from the lake. And because, once again, there were no obstructions here, it was able to wreck that subdivision. Look at what happens when it passes that subdivision. The damage path heavily weakens, and then it goes over water again. So it became strong for a little bit as it went over water, but then it went over land again, hit that home with the blue tarp in the distance, and then, if we go back to the map, all the water, help that it had, completely vanished. Once the tornado made landfall again, it no longer had water to its south to offer RFD a free path into the tornado, and all the damage post-lake landfall was EF0 to EF1. In other words, the lake was the reason why this tornado was able to become so strong, because water offers no friction to an RFD axis and ability to wrap around a tornado. One more thing I wanted to say before this video ends, it's always really difficult, and I just wanted to, when a tornado does damage this bad, and I just wanted to express my sorrow and that it's just really hard to, see and talk about these things. It's always important to remember the human aspect to every tragedy, and especially when a tornado this bad happens, it hits pretty hard. And I just want to extend my condolences to all the victims and everybody who was affected by this tornado in a negative way. Thank you for watching this video, and I hope you found this video helpful, and hopefully you will watch some more of my videos in the future. Thank you!